Right, hello and welcome back to another video. Now in this one we're taking a look at a very important result, namely that the area of a circle with radius r is pi r squared. Now this is one of them formulas that you're sort of taught to just memorize really and just use and be able to use it, but to understand the greater importance of it is just fascinating. Now the rigorous proof does require some calculus, namely some integration, but this isn't too bad. And I'm going to sort of do this proof two ways. They're both essentially the same, but one might appeal to the more GCSE students, and the other might appeal more to those who have done calculus. They're both essentially the same, just sort of worded slightly different. Okay, so let's draw a huge circle here. And what if we could somehow split this into loads of little rings of circles? So what I mean by this is let's create another circle within. So something like that. My picture's not perfect. And what if we try to work out the area of one of these strips? Okay. Well, perhaps you might see that if let's say we had some imaginary scissors and we made a cut here, and we sort of unraveled this ring, what we would actually get is a rectangle. Okay. And what would its width and length be? Well, this is the outside of the circle, so its width would be the circumference, which is 2 pi r. And we'll talk about its width in a bit more detail in a moment. So, here's what we're going to do. We're going to partition the circle into infinitely many rings, and I'll explain what I mean by infinitely many rings in a moment, and then unravel each ring. Okay, and this might seem really abstract at the moment, but this is more for intuition rather than being a rigorous proof, so just bear with me and then unravel each ring. So let me explain what I mean by this. Okay, so here's my diagram, and again it's not perfect, and of course it's never going to have infinitely many rings, but now note that the distance from the center to the edge is still r, so it's still a radius, and let's now unravel each ring. So we start by unraveling this one, and then this one, and then so on. So I'll do that and then we'll have a look at what's happened. Okay, so again, reminder of the method, we're going to unravel each of these rings, okay, and now in practice there'd be infinitely many, but for the sake of my diagram we've kept it nice and simple. A few things to note. So note the width of each is the same. So the width of each ring is the same. And of course, the circumference of a circle is 2 pi r. Okay, this is really important. I mentioned it earlier, and now the magic is going to come together. So I've unraveled each ring. So imagine we place a cut down where these blue lines are, and we sort of unravel both ways. This is what we're going to end up with. Okay, so this is it. We've got our biggest ring at the bottom. And remember, the biggest ring went around the outside of the circle, which means that the distance from here to here is going to be 2 pi r. Okay? And finally, if you remember, the distance from the center of the circle to the edge was r, which means the distance from, the middle of our bottom ring to the top is also going to be r. Now let's imagine for a second that there are infinitely many strips or rings, and you can sort of imagine that these edges would be a bit more, smooth and rounded off, and similarly down here. And this is where the magic sort of happens, as it were. We've now created a triangle. Okay, so we've got a triangle with base 2 pi r, so pi there, and height r. Okay, so what have we done? To get from this circle down to here, we just unraveled. Okay, we've unraveled each ring. And now a ring sort of approximates a rectangle. Okay, and this is where it gets a bit technical. So it's a rectangle. So it's a rectangle of small width. If you imagine there's infinitely many, each rectangle is going to have to be super thin for this to work. So what have we done? We've transferred finding the area of a circle to now just finding the area of this triangle. So the area of this triangle is just a half times the base times the height. But we know the base and the height, that's just a half times 2 pi r times r. And here we go. The 2 and the half cancel. Pi times r is just pi r squared. So there it is. There's sort of an intuitive way of thinking about the area of a circle. And now we'll sort of put this into a bit more of a rigorous setting and use some calculus to, nail down the proof. Okay, so in terms of calculus, what have we done? Well, calculus, or rather integration, is all about, or Riemann integration certainly, is all about approximating areas under curves by rectangles and then letting these rectangles get really, really small and really, really thin. So hopefully the approximation is very, very close to the true area. And if you think about it, unraveling this circle with loads of rings, I sort of call that method we just did the onion proof, because onions have a lot of layers, yes, and we've sort of split the onion, or we've split the circle into loads of layers, and then we've unraveled to form this beautiful triangle that has base 2 pi r and height r. So essentially what we've done is we're now looking for the area under the curve of the line 2 pi t, where t is our integrating variable, and we want this to go from a very, very small rectangle, 0, and we want it to go up to our biggest radius, which is r. Okay, applying the fundamental theorem of calculus, as in finding an antiderivative for this. Well, this is simple. It's just going to be 2 pi, that's constant. The antiderivative of t is t squared over 2, and we just need to evaluate at t equals 0 and t equals r. Again, so if you've not seen calculus before, this may look really, really strange, but it's really not as bad as it looks, and it's all very intuitive. So 2 pi. When t equals r, we just got r squared over 2. And when t equals 0, we just got 0. So evaluating this, again, we just get pi r squared. And what does this mean? Well, actually, dt is this really small width. Okay? And 2 pi t is the length of each rectangle. So instead of doing this as the area of a triangle, we're now just summing up all of these rectangles individually, starting from the very smallest one, when it's right at the top and it's not got any width at all, and we're going down to the bottom one where its length is r. Yeah. Okay, so amazing. We've sort of given an outline and an intuitive proof as to why the area of this wonderful shape we have, the circle, why the area is pi r squared. Really hope you enjoyed this video. This is really fun to make, and yeah, I know my diagrams aren't the best, but hopefully you get the idea. If you've made it this far, please leave a like. It really does help, and of course subscribe if you haven't already. A lot of people who watch my videos aren't currently subscribed, so yeah, please go ahead and subscribe. Thank you all very much for watching. Bye bye.